Okay, so our final contributed talk for this session will be given by Guan-Lin Liu, a PhD student from the Department of Chemical Engineering at Imperial College London. Here you go.
Hello. Hi, everyone. I'm Guan-Lin Liu. I'm the final year PhD student supervised by Professor Sergei Kazarian. Today, I'm very happy to talk about a recent research we collaborated with Heritage Collections at UK Parliament. And my PhD research focuses on application of ATR-FTIR spectroscopic imaging in the investigation of cultural heritage objects. And today I'm going to talk about the research that we investigate a white crust found on the painting, which were produced by the painter Edward Poynter. So here on the slides, you can see an outline of my presentation. I'll begin with the background of the painting, and then I'll introduce a type of very common degradation products called metal carboxylates or metal soaps, which is highly associated to the white crust issue. And then I'll talk about the results of the ATR-FTIR spectroscopy imagery results coupled with SEM index results. And then I will briefly talk about the treatment of white crust removal, although I was not involved in this work, but I think by mentioning it can make the presentation complete. And I will conclude the key points, the key results in this study. So in 1847, yes, the Fine Arts Commission led by Prince Albert embarked on a plan to redecorate the Lobby Hall at the Palace of Westminster with 4 monumental mosaics after the fire accident. And the painter, Edward Poynter, was responsible for 2 of the painting. And this painting, because it was used as a tool for making mosaic, so it was not for exhibition. And this painting, due to the long distance transportation between Italy and England, and also very poor storage conditions, this painting has been observed a very serious problem of white crust on the painting. So you can see that the pictures, that there's some white crust formed on the painting. And we extracted 4 locations of the paintings to make cross-sectional samples to investigate the strategies samples. So our primary tool is ATR-FTIR spectroscopy imaging, which allow us to acquire spectral and spatial information simultaneously into 2-dimensional chemical images. So, for example, that this is the chemical images of this area of the cross-sectional samples. And by extracting 1 pixel, we can have their spectrum, and we can interpret it and identify the components. So this slide illustrates how these chemical images were produced. For example, that this is the spectrum of calcium carbonates, and we select this characteristic band. We integrate this band at from 850 to 890 inverse centimeters, and we plot this integrated absorbance into chemical images. So each chemical images represents the distribution of different components in the cross-sectional samples. So I would like to introduce a very common degradation product called metal carboxylate, mostly found on the oil paintings. They result from the interaction between metal ions which come from pigments, and the fatty acid which come from binders such as secretive oils. And this kind of degradation may cause some problems such as protrusions on the surface of the painting, or they can even aggregate as crystals within the paint layers. And much of the literature on the metal soaps, they rely on FTIR and Raman spectroscopy. In FTIR spectroscopy, we can detect the metal soaps by identifying the carboxylate band at the wave number region between 1500 inverse centimeters to 1600 inverse centimeters. And Dr. Hermes has researched these metal soaps for quite a long time, and you can, if you're interested, you can refer to his publication. And this is the illustration pictures of how the formation of these metal soaps form during the drying process. So let's move on to the results of this study. This is the first samples extracted from Harmony's hair. And from the picture B and C, that you can see that the chemical images of the sulfates. So we detected sulfates in the white crust area. Oh, sorry, I forgot to introduce this. This is the microscopy of the cross sections. You can see that there is a thick white crust accumulated on the paint layers. And as I said, that these components mainly contain sulfates. And by combining the results from ACN index, we found the distribution of lead in this area. So we can confirm that this sulfates should be lead sulfates. And apart from lead sulfates, we also detected small amount of calcium carbonates. That is also confirmed, supported by the SEM index results, where we can see the distribution of the calcium. And additionally, we also detected two types of metal soaps, the crystallized and amorphous one. The crystallized is mainly lead soaps which are located in the ground layer, while the amorphous metal soaps shows the broad band of carboxylate band at 1500 inverse centimeters to 1600 inverse centimeters. And this kind of amorphous metal soaps mainly distribute in the paint layer. And the second samples extracted from St. David's cloak, they also have this white crust problem. And we identify metal oxalate and sulfate on this white crust layer. And by combining SM results, we may assume that the metal oxalates may be calcium or lead based. It's not very easy to tell which one because they may overlap. And also, calcium oxalate is the most common oxalate found on cultural heritage objects such as oil paintings and sculptures. So we did not want to exclude the possibility of calcium, although you may not see that very clear distribution of calcium in the region of the white crust. And again, we also detect the crystallized and amorphous metal soaps distributing in different areas. And the third samples extracted from Harmony's cloak, we did not detect the continuous and thick white crust as we can see from the previous samples, but we do observe some localized white crust, and this has been identified as calcium carbonates, also supported by the SEN index results. And we also did not detect we also did not detect lead soaps and also amorphous soaps as we can see in the previous samples. And in these samples, we detected crystallized zinc soaps, which you can see from its spectrum that the very characteristic band at around 1527 and 1539 inverse centimeters. One of the interesting findings in this part of the samples is that we detect lead and antimony. So this suggests that the artist may use Naples yellow, which is a lead-based pigment, just like lead white is toxic, and it's very prone to degradation due to its sensitivity to environmental factors such as light and air pollutants or temperature, humidity. And I'll explain in the next slides, because this, as I said, that this Naples yellow is lead-based pigments that can cause different degradation products. So in the next slides, it also contained that lead and antimony. So the artist used Naples yellow, and from the white cross, I'm not sure if I should call it white cross because it seems like very complicated. And you can see that, sorry for not very clear microscopic images, but in this microscopic image, you can see that there's a darkened area and some grayish or the white cross here. And from the chemical images results, we detected a variety of components in this area. Firstly, we detected lead sulfide and lead sulfate, which may contribute to the grayish and darkened area. And also, we also detected metal oxalates, alongside with calcium carbonates and gypsum in this region. And we also detect abundance of zinc soap in the paint layers. And as I said, that the Naples yellow may be contributing to the cause of the complex degradation in this on the surface of the painting. So, because sulfates were detected both in the white cross area and the ground layer, but with the spectrum of ATR-FTIR, we can distinguish these two components, although they're both sulfates. The one in the white crust, it is lead sulfate because we can see carefully at their spectrum that they have the spectral band at 964 inverse centimeters, while the sulfates detected in the ground layers should be barium sulfates because it has the sulfate band at the larger wave number at 984 inverse centimeters. So by comparing and look carefully into the spectrum, we can distinguish the degradation products from the original materials. So I would like to talk about the diffusion of lead from the ground layer to the surface of the painting, because there was an assumption that the lead soaps can migrate from the ground layer to the surface of the painting. But Dr. Hermans challenged this theory because he had two reasons. The first reason is that the crystallization of metal soaps is irreversible, so it's not very possible for the crystallized lead soap to become amorphous soaps and then relocate through the paint layers. And the second reason is that lead soaps are insoluble, so it's not possible for the lead soap to diffuse through the paint layers. And he proposed, Dr. Hermans proposed a theory called ion jumping, which means that the metal ions in the ground layers can jump as an ion in the ionomers, which is a complex that conjugates with different metal ions. So the metal ions can jump by this mechanism towards the surface of the painting. And our paper is the first paper to visualize this mechanism, because we mainly observed that the crystallized lead soap in the ground layers, and we did not detect any crystallized lead soap in the pigment layer, while we detected amorphous soap, which can be seen as ionomers, the complex for the ions to jump or diffuse to the surface of the painting. And while the lead diffuses from the ground layer to the surface of the painting, the iron reacts with the air pollutant to form white crusts, such as lead sulfate and lead oxalate or calcium oxalate. So this is how we use the ATR-FTIR spectroscopic imaging to illustrate this mechanism. So because we have identified the main components in the white crust, so we have reported to the conservator, and they use 2% ETDA. It is a lead and calcium chelator. So they apply this ETDA on the surface of the painting and then wash away the white crust. So this is the before and after treatment pictures of these paintings. You can see from the picture that Harmony does not have white hairs. So many details can be seen from these paintings after the treatment. So the conclusion, we successfully identified 3 components in the white crust layers, and we also visualized the mechanism that the metal ions diffuse from the ground layer to the surface layer using ion jump mechanism. And we also detected original materials and other degradation products by providing their chemical distribution information. And we know that lead plays a crucial role in the formation of white crust, either when there's a lead white used in the ground layer or they use the lead-based pigments such as nacreous yellows. So we would like to thank to these people that contributed to this research, and thank you so much.
All right, thank you very much, Guan-Lin. Do we have any questions before we break? Yeah.
Thank you. I wondered if you could say anything about how quickly you think those metal crusts, the white surface blooms, might reoccur, because you've obviously got metal soap still in the ground layer. Do you think the iron hopping process will continue to happen and that those disfiguring crusts will reform?
If I understand your question, you mean that if this diffusion of lead will continue happening? Yeah, I think the answer is yes. So conservation is very important. But it's also, because I don't think that this problem is very serious. I mean, because these paintings were not used for exhibition, so they were poorly conserved, poorly storage. But according to the curator at Heritage Collections at UK Parliament, they say they probably will consider to exhibit this painting, so there may be good care and good conservation. So I think the problem will not be as serious as this one. Yes.
I'm assuming that the paintings were unvarnished, yes?
Yes.
And
yes.
We have crust directly on the paint layer. I was wondering, and I know it's not part of this research project, but if the painting was varnished, would that hinder, stall, or affect, the formation of white crust? Do you know anything about that?
You mean if we
had a farther surface layer, assuming that there's constant migration onto the surface of the crust, does that affect it? Would that affect it if the painting was varnished?
Yes, I think that if the painting is varnished, the white crust may be avoided, because that we know that the lead ion reacts with the air pollutants such as sulfates, SO2 or CO2, to form the white crust. So I think, yes, I agree with you that this can prevent the white crust happening, but we still cannot stop migration of lead whites. Yeah.
But we could hinder it to some degree, right? By applying a surface.
Yes, you're right. We could hinder this white crust issue by, apply the varnish. Thank you.
Thank you.
I noticed that in some of your X-ray maps you showed antimony. Is that used as a pigment, or is it just an artifact or a contamination, or what's the antimony doing?
Yeah, this is the oops. Yeah, we really had a debate, not debate, a discussion with the reviewer of this paper, because they doubted that the identification of antimony, but because the X-ray characteristic, the characteristic X-ray of antimony is very close to calcium, so they may be misunderstood. But we look carefully at this antimony, this element, so we are pretty sure that it is the detection of antimony. And for your question, we don't think that it's a contamination, because you can see from the SDN results, it's like it's abundant everywhere in the pen layers. If it's contamination, it would be like calcium is on the surface of the painting. So, and this antimony was just like some of the components of this Naples yellow, which is lead and antimony-based pigments. Yeah, so it's the original material from the pigments the artist used, which is, I remember that this kind of Naples yellow has stopped using before the late 19th century. Yeah, so it was used in a very short period of time.
Just a comment, Roman glass often has antimony as well.
Oh, cool. Oh, it's common.
Okay, awesome. Thank you very much again, Guan-Lin. So thank you. Ooh, yep.